Humans have long been intrigued by the concept of creating autonomous machines that resemble us. When these machines need to interact closely with us, there's a preference for them to have a familiar appearance. Currently, most humanoid robots mimic the human body's shape, usually including a torso, head, 2 arms, and 2 legs, although some replicate only specific parts of the body. These robots fulfill diverse roles, ranging from practical tasks such as using human tools to experimental studies like exploring bipedal locomotion. Androids, in particular, are humanoid robots crafted to visually resemble humans. While humanoid robots are increasingly integrated into industries like logistics, manufacturing, healthcare, and hospitality, fully functional cyborgs remain a distant prospect. However, scientists are pioneering new ways to blend human and machine capabilities. The humanoid robot market was valued at $1.8 billion in 2023 and is projected to exceed $13 billion in the next 5 years. This growth is driven by advancements in AI and the development of humanoid robots with more human-like features, enhancing their ability to take on diverse roles in fields such as service, education, and healthcare. Scientists are developing new methods to make robots appear more human-like by attaching lab-grown skin. This breakthrough, pioneered at Tokyo University, involves using collagen-coated robots with drilled holes, allowing the skin to adhere naturally and move realistically. The technology aims to bridge the uncanny valley, where robots appear unsettlingly non-human, potentially leading to lifelike facial expressions. This research, featured in Cell Reports, Physical Science, introduces skin that can self-heal, raising questions about its future applications beyond robotics. Scientists at the University of Tokyo have also devised a method to effectively attach artificial skin to robot faces, maintaining mobility and enhancing the lifelike appearance of androids. This innovative approach involves mimicking human anatomical features such as muscles and ligaments on the robot's surface. Beyond improving android aesthetics, this technology shows promise for applications in fields like cosmetology and plastic surgery. Using a human facial mold with perforations, researchers applied a gel made from collagen in dermal fibroblast cells, allowing it to permeate the perforations and securely adhere to the mold. This process resulted in a simplified version of human skin that can stretch into expressions like a smile when manipulated by connected rods, thus achieving a more natural appearance. Future advancements are aimed at replicating additional features such as sweat glands, sebaceous glands, pores, blood vessels, fat, and nerves to further enhance the realism of synthetic skin. Now let's explore the advanced processes behind creating top-notch Korean implants and prostheses. We'll begin with the cutting-edge manufacturing of silicone foot prostheses using state-of-the-art 3D printing technology. It starts with a precise digital scan of the patient's foot to capture exact dimensions and contours for a tailored fit, ensuring maximum comfort and functionality. Next, the scan data is used to develop a refined 3D model of the prosthetic foot, optimized for both aesthetics and performance using CAD software. Once finalized, this model is sent to a 3D printer which constructs the prosthesis layer by layer, using medical-grade silicone for its durability, flexibility, and natural skin-like appearance. Following printing, the prosthetic undergoes meticulous finishing steps including trimming, polishing for realism, and application of lifelike skin tones and textures by skilled technicians. This attention to detail ensures the prosthesis not only functions well but also matches the patient's skin color seamlessly. The fitted prosthesis is adjusted as needed to achieve a perfect fit, crucial for comfort and everyday use. This fitting process may involve several trials and follow-up appointments to monitor and optimize performance over time, adapting to any changes in the patient's residual limb. Korean expertise in 3D printing technology continues to advance, making high-quality prosthetics more accessible and personalized. These innovations not only accelerate production but also enhance customization and precision, significantly improving the quality of life for amputees worldwide. In Korea, the mass production of humanoid robots has captured widespread attention online. Spearheaded by the company Service Look, these robots are set to feature in an animatronic installation at Gentle Monster, a local designer glasses brand.
The robots, manufactured using SLA wide format 3D printing technology, boast remarkably realistic finishes, enhanced further with urethane coating for durability.
Achieving lifelike skin textures involved applying high-resolution textures down to the pores, followed by extensive post-processing to achieve natural skin tones. The production process begins with engineers designing 3D models using CAD software, followed by preparing and calibrating the 3D printer. Components such as bodies, limbs, and other parts are then printed using various materials. Assembly involves integrating these parts into a functional unit, including attaching limbs, installing motors, sensors, and performing wiring. Rigorous testing ensures the robot meets specifications, with iterations possible until satisfactory performance is achieved. Despite their realistic appearance, these robots are currently non-functional art pieces, yet they serve as powerful ambassadors drawing global attention to robotics. Researchers in robotics have long explored artificial skin to enable robots to sense their environment. A major challenge has been the immense computing power required, similar to processing information from 5 million receptors in human skin. Scientists at the Technical University of Munich developed a groundbreaking approach using robot skin cells and a sensing system inspired by human skin. This innovation reduces computing power by activating processing only when cells detect stimuli, akin to how our brains process sensory signals. This breakthrough allows for extensive application of robot skin across humanoid robots, enhancing capabilities such as balance and interaction in scenarios like assistive care, opening new possibilities for human-robot interactions. Robots are also making remarkable advancements in the beauty industry. Loom robots, equipped with computer vision and AI, are now active in California beauty salons. These robots meticulously apply each eyelash individually within 15 minutes per eye. While the setup time totals 50 minutes, the process remains one-third quicker than a human's pace. Developers assert that clients find the process extremely swift, comfortable, and consistently effective. Experienced Korean artisans with over a decade of expertise meticulously craft highly realistic prosthetic eyes through a detailed consultation and assessment process. Using advanced 3D scanning technology, they create a precise digital model of the patient's eye socket for custom fitting. The oculist selects durable materials like high-quality acrylic or medical silicone, molding them into the eye's shape. The most artistic phase involves hand-painting the iris and sclera to replicate the natural iris colors and patterns with fine brushes and specialized paints. Each iris is meticulously matched to the patient's other eye, capturing subtle shades and intricate details. After painting, the eye is polished to achieve a natural sheen, and a clear coating is applied for protection and a lifelike appearance. During fitting sessions, adjustments are made for comfort and mobility, ensuring a natural fit in the socket without irritation. Regular maintenance, including cleaning, polishing, and checkups, preserves the prosthetic eye's condition and fit over time. Korean specialists demonstrate precision and skill, enhancing patients' physical appearance and quality of life with prosthetic eyes that blend technical expertise and artistic finesse to closely resemble natural eyes. Korean specialists employ advanced techniques to create highly realistic and functional prosthetic arms through a meticulous and multi-stage process. It begins with a detailed consultation and measurement phase to assess the patient's needs and physical condition. Precise molds are taken to ensure a comfortable and secure fit. Next, a customized 3D model of the prosthetic arm is designed using advanced software, incorporating specific anatomical details. This model guides the 3D printing of main components, which are then assembled with high-tech sensors and microprocessors. These components enable the prosthesis to replicate natural movements by detecting electrical signals from the user's muscles. Once mechanical assembly is complete, the prosthetic arm is covered with silicone skin, meticulously painted and textured to resemble natural skin, enhancing both aesthetics and realism. During the final fitting, adjustments are made to ensure optimal fit and function for the user. Training sessions follow, allowing the user to learn to control their new limb effectively, restoring independence and functionality. Throughout the process, close collaboration between the prosthetist and patient ensures personalized adjustments and addresses any issues, tailoring each prosthetic arm to the user's unique needs. In summary, creating a realistic prosthetic arm blends advanced technology with expert craftsmanship, resulting in a highly functional limb that enhances mobility and independence for users in their daily activities. Researchers at Pennsylvania State University achieved a breakthrough by directly printing multi-layered living skin onto an open wound using a 3D printer. This pioneering method includes regenerating hair follicles, which is a unique capability. Human skin comprises 3 layers: the outer epidermis, the middle dermis, and the deepest hypodermis, which provides structure and support. The bioink used in the printing process consisted of human adipose tissue-derived protein molecules for tissue structure, stem cells from adipose tissue for regeneration, and a fibrinogen-containing solution for clotting and binding. Using a specialized bioprinter with 3 compartments, researchers simultaneously deposited these components with precise control onto the wound, facilitating the formation of the hypodermis crucial for healing, temperature regulation, and hair follicle formation. This technology holds promise for aiding individuals recovering from head injuries and other wounds, potentially advancing healing and regeneration processes significantly. A biotech startup named BrainBridge, an U.S. startup led by Hashim Al-Gili, a molecular biologist, blogger, and screenwriter based in Germany, is pursuing robot-assisted head transplants within 7 years. Al-Gili, recognized for proposing artificial wombs in a previous baby factory concept, now advocates for a robotic system capable of transplanting a head onto a donor body while preserving brain function. The startup aims to conduct its initial operations within approximately 7 years. This visionary endeavor echoes the plot of a science fiction thriller, involving multi-armed robots guided by artificial intelligence. These robots delicately detach a living brain-containing head from its original body and transplant it onto a donor body, ensuring seamless connections to the spine, nerves, and blood vessels. Additionally, the startup plans to pioneer cosmetic surgeries such as face and scalp transplants with enhanced compatibility to minimize rejection risks. This innovation offers hope to patients grappling with conditions like stage 4 cancer, paralysis, and neurodegenerative diseases such as Alzheimer's and Parkinson's. Despite the medical community's initial quiet reception to this announcement, similar concepts have been proposed previously. For instance, Italian Dr. Sergio Cannavaro aimed to initiate head transplants as early as 2017 but only managed partial transplants of cadaver bodies. Scientists foresee the eventual feasibility of head transplants, with BrainBridge potentially realizing this vision, though likely not within the next few decades. Currently, reconstructive surgery and implantation techniques are limited to small segments like fingers or hand fragments. Experienced surgeons stress that head transplants present greater complexity compared to other procedures. Unlike surgeries involving single nerves, head transplants require meticulous connection of the spinal cord, which comprises numerous individual nerves. Consequently, nerve impulses travel through the spinal cord via specific bundles, each requiring precise connection for functionality. However, spinal cord reconnection is just one of many challenges. Even if successful, ensuring adequate blood supply to the entire head remains a significant subsequent hurdle. After carefully reconnecting the spinal cord, the surgeon faces the intricate task of stitching together the 12 pairs of cranial nerves, which independently control vital functions such as heartbeats, diaphragm movements, and essential muscle actions like those of the intercostal muscles crucial for breathing. Ensuring these vital organs function properly adds another layer of complexity to the procedure. For example, damage to the facial nerve could result in partial facial paralysis, impacting movement and expression on one side of the face. In cases of severe nerve trauma, such as to the facial or trigeminal nerves, the damage may be irreversible, making surgical repair impossible. This raises significant ethical concerns, as a brain transplant essentially involves transferring an entire body, prompting debates over whether it is ethically justifiable to save one life by using an entire donor body. Alternatively, should the donor's organs be prioritized to save multiple lives? Moreover, the complexity of brain transplantation increases the risk of rejection and potential mortality for the recipient.
Theoretically, transplanting the brain along with the head without removing it from the skull is a possibility, as demonstrated by experiments involving the transplantation of a second head on animals. However, the survival of these animals has been limited, with most living only from a few hours to a few days, and exceptionally, up to a couple of months. While some experts suggest human brain transplants could be on the horizon, neurosurgeon Frederick Meyer from the Mayo Clinic in Rochester, USA, remains skeptical, stating, "I doubt any surgeon or scientist would undertake such a procedure. I do not foresee it happening." However, as previously mentioned, the head transplant project is not the only ambitious endeavor on Hashim Al-Jili's agenda. Recently, the scientist unveiled Project Ectolife, which envisions a factory for human production or a human farm, depending on your perspective. Al-Ghazali, spearheading this innovative initiative, revealed details in an interview with Science and Stuff. The concept is poised to materialize in the coming years. The Ectolife project is a large-scale initiative aimed at cultivating human embryos to specification within specialized capsules, essentially artificial wombs. One envisioned facility comprises 75 laboratories outfitted with advanced technology, each accommodating up to 400 artificial wombs. This capacity allows for the production of up to 30,000 babies annually. Embryos within the facility will be available for access 24/7. Furthermore, parents will have the capability to continuously monitor their child's condition and development, including live video streaming from the artificial womb through a dedicated mobile application accessible worldwide. As an alternative, the Ectolife project also offers the option of placing the artificial womb directly in the parent's home, enabling the embryo to develop in a domestic setting. Prior to placing the embryo in the artificial womb, conception will be achieved through in vitro fertilization, a process where female and male gametes are artificially combined outside the mother's body. At this stage, parents can select the most viable and genetically optimal embryo for further development. Despite the seemingly futuristic aspect of this technology, Mr. Al-Ghazali highlighted that similar advancements have already assisted scientists in correcting genetic mutations linked to heart conditions in human embryos. Artificial intelligence will play a crucial role in the upbringing of these children. It will be tasked with customizing a personalized nutrient mix for each embryo, tailored to their specific developmental needs. This technology will also enable adjustments to the composition of artificial amniotic fluid based on changing circumstances. Furthermore, artificial intelligence will monitor the children's development and promptly alert caregivers to any anomalies in the embryo's condition. Furthermore, this new technology will allow for prompt treatment of any future pathologies in the child, without posing risks to the mother. Another significant benefit of the human production facility is the capability to conduct experiments on embryos when needed. For example, Mr. Al-Ghazali pointed out that during the 9-month pregnancy period, a child may not have sufficient time to fully develop. Premature expulsion by the mother's body due to strain can leave the newborn vulnerable for an extended period. However, cultivating the embryo outside the mother's body could potentially address this constraint. Parents will not only be able to monitor their future child's condition via an application but also to fully experience what the embryo sees and hears inside the artificial womb. Equipped with 360-degree cameras, the capsule transmits video and sound to a virtual reality headset. Moreover, the artificial womb is equipped with speakers that allow parents to communicate with the child, play music, and introduce spoken words. This interaction enables the child to engage with their environment and become familiar with their family even before birth, similar to the experience in a natural womb. In the case of artificial gestation, the birth of the child will occur seamlessly, simply with the push of a button, draining the amniotic fluid from the artificial womb and welcoming the child into the world. The human production facility could offer a viable solution for many couples experiencing reproductive difficulties who, for personal reasons, prefer not to adopt. Additionally, artificial embryo cultivation reduces health risks for women, mitigating pregnancy complications, miscarriages, and maternal mortality during childbirth. The project's creators have also prioritized environmental sustainability. Ectolife laboratories will operate on renewable energy derived from solar and wind power, leveraging cutting-edge scientific advancements. The Ectolife project is no longer confined to the realm of science fiction.